All right, let me go over these next few days. See if you guys have any questions. So this morning I had a help session. I will going over some related rates. I think worksheet 2. So I will upload that on the website later this afternoon. The quiz was supposed to be tomorrow, but we're going to flip-flop tomorrow and Wednesday. So today we're going to do quiz review, or it says test review, but this year is going to be quiz review worksheet 1. And whatever we don't finish, hoping that we can do some of that tomorrow. So tomorrow we'll go over 3.1. We'll start the next section, which is not on the quiz, but it allows us to, or allows you to get an extra day to review without losing a day of instruction. So flip-flop the Tuesday and Wednesday. So tomorrow we'll go over 3.1. It won't, I don't think it'll take the full period, so that's good. We can use the second half of class to continue reviewing for your related education. There is homework for 3.1, but 3.1 homework will be due on Thursday. Not due on Wednesday. I'm not going to be checking homework on the day of the quiz. Okay. Also, I will have a help session Wednesday morning. So tomorrow morning, I think help session with my pre-calc students. So Wednesday morning, I'll have help session going over worksheet 3, and that'll be 7:15 a.m. And I'll send out a reminder this afternoon. Okay. Also, I want to share this with you. These are the test topics. I have this on my website, and also I'm going to send this to you through Remind this afternoon. Okay, so don't feel like you have to write this down, because I'll send this list to you. So let's just kind of go through these here. Either volume, surface area, or area circumference. Either way, it's equation. The problems where you got to find a derivative of 2 separate equations, and once you get down to the derivative, you're just kind of matching them to see what, or using the equations given and the derivatives you found to see if you can find a way to get to the answer, whether it's like ds dt or it could be dr dt. We've done a couple of those, so hopefully, and we'll do a couple more today. Pythagorean theorem, word problem. We've seen enough of this, hopefully, and we'll continue to do and then get practice with those. Area of triangle, product rule. We saw this with the ladder problem, and we'll see another one with Pythagorean theorem problem asking you for the rate of change of the area. Data approximation we'll review today. L'Hopital's rule we'll review today. Cone problem. We've done quite a few practice with those. Hopefully you guys are getting more comfortable with them. I will give you the formula for the cone. And then cylinder problem. We talked about how cylinder is in a way easier, but it's also harder. Easier in the sense that it's easier to work through it. It's not as difficult as cones, but harder because it's easy to involve the steps for cone and force it into the cylinder problem, which makes students miss those problems. So we'll go over one of each today. And then shadow problem. I don't think I'll get to a shadow problem today, but we'll do a review tomorrow. Okay, so those are a list of your quiz topics. You will get to use your calculators. You'll have a full period to work on it on Wednesday. Any questions?
So the only formulas we really need to know are like the Pythagorean theorem and the rule.
Yeah, Pythagorean theorem, know the shadow problem setup. L'Hopital's rule, know that linear approximation. Yeah, but all the geometric stuff I'll give you. But yeah, Pythagorean theorem, there's no area triangle you need to know. But everything else, I geometric I'll give you. Okay.
Thank you.
All right, so, if we, no further questions, let's go to page 5 in your new test packets, test review packet. Is anyone missing this packet? I think everyone picked one up last week. It has, 3 test reviews in it, and it has all the keys. Yeah. Yeah. Okay, so page 5. Let's go ahead and set up this problem. This is a Pythagorean theorem problem. Go ahead and read the problem, see if we can set up this diagram here. Okay, a balloon is rising vertically above a level straight road at a constant rate of 1 foot per second, 1 feet per second. Okay, what can we assign this to? Yeah, dy dt, right? We see feet per second. We know that's a rate. Time has to be involved. Okay, positive or negative? Because good. Y is increasing, right? Not so much the rising part. It's the fact that the length of this height of this triangle is increasing, getting longer. Okay, just when the balloon is 65 feet above ground. Okay, I'll put that for Y for now, but we gotta put a star next to it because we may have to revisit that value later. Okay. All right, bicycle is moving at a constant rate of 17 feet per second. It passes under the balloon and then continues moving. Okay. So, what can we put that under? dxdt, okay. Positive or negative? Positive, because as he's moving away from that moment where he passes, where he's right under the balloon, that triangle, that base of the triangle is getting longer. Positive value. Okay, how fast is the distance between the bicycle and the balloon increasing? What are we looking for there? dZdt. Okay. That's the unknown. I'll put a question mark there. Okay. Now, something that we haven't seen before is having to use this information and how it can be important for helping us figure out some information. How is that 3 seconds later? Okay, so the idea is that we're imagining that we're taking a picture of this triangle 3 seconds after the moment that it passes under the bicycle passes by under the balloon. So how does that 3 seconds help us out?
We can multiply by 17, yeah, x.
Right, so it doesn't tell you explicitly what that length is, but it does give you information to kind of help you get there. So if we know how fast the bicycle is moving and how long, we can figure out how much distance is covered in that time interval. So like we said, 3 times 17 is what? 51. So the bicycle is going to be 51 feet away from that moment where he's under the balloon, because he's been traveling at 17 feet per second for 3 seconds. But there's something else we have to take into consideration. What's that? That y, right? That y is 65 feet when the bicycle is here, but when the bicycle is over here 3 seconds later, where's that balloon going to be? 68, because we got to add the fact that he's 3 seconds past, the balloon is still rising at 1 foot per second. So plus 3, which is 68. So that's a little tricky. But it makes sense, right? That the balloon is not just hanging out 65 feet and it's not just staying there, right? It's still rising, even as time passes. Okay, how can you find z? Pythagorean theorem, and then to find these dt, we just insert into the equation. So now it gets easier, right? But getting that x and y, using that 3 seconds later is what is different about this problem. Okay, see if you can finish this problem. Okay, so hopefully we found these steps to be pretty straightforward. Pythagorean theorem gets you that 85, and then the rest just insert into the derivative equation, and then just solve for d z dt. We're expecting a positive value because as the balloon rises and as the bicycle gets further and further away, we know that distance between them is growing. So that positive 11 does make sense. Any questions with one? Okay, number 2. Suppose f of x equals 3x squared minus 2x. Write the equation of the line tangent to the graph at x equals 2. Then use local linear approximation to estimate f of 1.9. So even though we're covering linear approximation and we're putting it on this quiz, it's really technically not a new topic. It's just that these are the steps for the combination of finding tangent line equation and then inserting a decimal value in. So you already know how to do most of it. Okay, so first thing is we're going to focus on the linear portion of this name of this concept, and that is finding that tangent line equation. So using the function and the x value, we can find the order pair, and then we can find the derivative. From the derivative, we can use the x value to find the slope. Once you have your order pair and your slope, you can put it in a point slope form. And then once you have your equation of your tangent line, then you just insert whatever decimal value they ask you to insert. So see if you can go through these steps with these instructions and see if that makes sense. And remember, at the end, you're inserting 1.9 in for x. Okay, this is your x value. Try those steps, and I'll follow up after you guys try it. Insert 2 directly into the function. That'll get you your y value. That's your order pair. Okay, next, find the derivative. Derivative, you can find the slope. Any questions so far? Okay, form your tangent line equation. Order pair goes in for x1, y1. Slope goes in for m. So once you have your tangent line equation, typically I find that's a little bit cleaner. Just move that 8 over to the right side, get that y by itself, and now you're ready for your approximation portion. Just insert that 1.9 in for x, get that decimal value, and that's your linear approximation. Okay, linear approximation is supposed to be easy, so hopefully you guys find it easy, because you already know how to do it. We're just giving a name to this process. Any questions of part A? Okay, part B, same concept, same thing, but what makes part B easier? Gives you everything you need, right? Gives you order pair, gives you your slope. So you can jump directly to this step. Okay, see if you can finish out part B. Guys, the key is attached to this packet, so if you're working ahead, you're more than welcome to do that. Any questions with part B? Okay, no questions. All right, number 3, find the limits. So we're bringing limit back because we want to talk about L'Hopital's rule, but we don't use L'Hopital's rule just whenever we see a limit problem, right? What's still the first step for every limit problem? Assuming it's a question real number. Got to plug in first, right? Because we got to know which category we're dealing with. Are we dealing with a real number? Are we dealing with a 0 over 0? Or are we dealing with particle asymptote, which is limit doesn't exist, right? We got to know which category we're dealing with. If we're inserting an x value, getting a real number, we stop, right? If we already have the answer, that's our limit. But if we get 0 over 0, that means it's an incomplete form. The limit is hiding inside the problem, but we're still not getting it. It's still not showing it to us. So that is when we use L'Hopital's rule, right? Use L'Hopital's rule when you see that there is a limit, but it's just not quite showing it to you. Okay. And obviously, if you get like 10 over 0 or 8 over 0, you also stop. But then in this case, you conclude that the limit does not exist. Okay, so first things first, for part A, we insert 3 into the function or into the expression. And what do we get? You get 0 over 0. We get a real number, right? So if we get a real number, then that's the limit. There's no need to do L'Hopital's rule. We don't do 8x minus 5 over negative 6x, right? That would be incorrect because if you try to do L'Hopital's rule and then plug in 1, you're not going to get the real answer because we need to confirm that you get 0 over 0 before you do L'Hopital's rule. You don't do L'Hopital's rule and then plug in the x value without confirming that you're getting that full graph. Okay, so no need for L'Hopital's rule for part A because we already have the limit. Okay, try part B. First things first, plug 1 into the expression. Here, what do we get? 0 over 0. Okay, so now we can do L'Hopital's rule. Now with L'Hopital's rule, you can take the derivative of the numerator separately, take the derivative of the denominator, and then reevaluate. So on the quiz, even if you get the right answer, I'm looking for 0 over 0. I want you to show me that you are taking that step and that you are fulfilling the condition before you do L'Hopital's rule. So show me that step. Show me that you are actively checking what that expression is before you do any other steps. Okay, so the derivative of the numerator, just a simple power rule step. Denominator, also power rule. Now reevaluate, and hopefully this will lead us to a real number. It does, we stop, that's our limit. Now, what if I evaluated the limit, I got 0 over 0, I did L'Hopital's rule once, and I re-evaluate and I still got a 0 over 0.
Do it one time.
And do it one more time. Okay. So each time I get a 0 over 0, I get the green light to do L'Hopital's rule once. Okay. But as soon as you do 0 over 0 L'Hopital's, you got to reevaluate. Okay. We don't want to jump into a derivative a second time without first confirming. This has to show up before we can do L'Hopital's rule.
Will there ever be questions where we'll have to do L'Hopital twice?
Potentially.
Let's see.
Now, we saw it in one of our practice problems. Okay, any questions with these two minor topics? Linear approximation and L'Hopital's rule. Okay, let's talk about number 4. Okay, let's talk about cylinders. Cylinder is the easier of the two between this and cone, but it's very different in the way that we approach it, right? Okay, so water is leaking out of a cylindrical container. At a rate of 5 cubic centimeters per hour. What can we assign that to? GBDT. And anything special about that?
Negative.
Negative, okay. The container has a diameter of 12 centimeters. And a height of 16 centimeters. At what rate is the height changing? What are we looking for? DHDT. And the water level has a height of 3 centimeters. Okay, here's our volume equation. Okay, what's the major difference between cones and cylinders for our related race problem? The radius is constant. Okay, so that is the big difference there. Now, they don't tell us the radius, but we can figure out that radius, right? What's our radius? 6 centimeters. Okay, the radius is constant. And the difference there is that with cones, we had to hold on to our R variable till the very end of the problem. Here, as soon as we know what the radius is, we can go ahead and replace it, because you can imagine that radius of the water level, doesn't matter if it's half empty or completely empty or full, it's going to stay the same all the way through. There's no need to hold on to this variable if it's going to stay the same value the entire problem. So just by doing 1 or 2 steps, you're ready to do your derivative. Okay. With cones, we had to go through a lot more to get to this point, but now we can jump directly into our derivative. V becomes (36 pi stays). H becomes, okay, no similar triangles, no R over big R equals little h over big H, which means that we have some information that we don't need, right? So what information can we just, is not part of our problem? The height, right? These are great for cone problems, but it's not necessary for cylinder problems. Okay, so now just replace dVdt with -5 and then solve for dHdt. Again, careful that pi is going to land in the denominator. It needs to stay in the denominator even with your answer. What's our unit of measure? Okay, next page, number 6, page 6. Another Pythagorean theorem problem. Okay, so the boat is drawing closer towards the dock. The rope that is on the dock is pulling the boat in. And then the boat is going to be 6 feet below the dock, or the water is going to be below 6 feet below the dock. Okay, so let's read the problem here. Boat is being pulled towards the dock by a rope, 6 feet above the bow. What's that? That's the Y. The rope is hauled in at a rate of 2 feet per second. dCdt. Anything special about that? Negative, because this is getting smaller. The hypotenuse is getting smaller as the boat is getting pulled closer towards the dock. How fast is the boat approaching the dock? dxdt. We're talking about the speed of the boat in relation to the water, so dxdt. When 10 feet of rope are out. Z, right? The rope is here. Okay, how can we solve for x? Yeah, Pythagorean theorem. This is a variation of the 3, 4, 5 right triangle. And what's dy dt? 0, because that distance is never going to change, right? X is going to get smaller, z will get smaller, but that set distance is not going to change. That y distance will stay 0. Sorry, it will stay 6, so therefore the rate of change is 0. Okay, we should have everything that we need. Oh, and then x is what? 8. Okay, so use your equation. Okay, making the calculator do all the work for you from here on out. Rate of change, units of measure, feet per second. We're getting a negative rate, that makes sense, right? As the flow gets pulled closer, that x, the horizontal distance is gonna be shorter. Okay, part B, at what rate is the area of a triangle changing? Okay, what variable are we looking for there? The ADT, right? But first we have to build the area of a triangle, right? What's the area of a triangle? Yeah, 1/2 x times y. Okay, 1/2 base times height. So we build that first. But we know we got to find the derivative, right? dAdt. Anything special about that 1/2 xy? What's needed if we want to find the derivative? If I go through a product rule, yeah. So see if you can go through product rule. Try it on your own first. See if you can successfully build out the derivative, because once you build it out, then it's import everything from part A and find your dAdt. Okay, so try that first. I'll go over it with you. Okay, let's talk through it here. What's f prime? One half. What happens with the x? Goes away, but anything that comes after that?
Yeah.
Remember, this is related rates, right? So we gotta have every variable still impacted by time. So 1/2 dx dt, right? Now, normally we would just do 1/2, but now with related rates, time is the independent variable. We gotta attach d over dt for every variable, even if they disappear. Okay, g is just y, no changes. F is just 1/2 x, no changes. And what's g prime? Good. Right, so don't forget about your d over dt's for each of your variables. Okay, so that's the hard part, right? Recognizing product rule, applying product rule correctly. Now you're just taking all the values you got from part A and inserting them in. Okay, units of measure, dAdt, area is square feet. Time is seconds, so therefore square feet per second. Okay, number 7 is a cone problem. We practice multiple times, so see if you can work a cone problem from beginning to end on your own. I'll do similar triangles. Replace one variable in terms of the other. Right, all those steps. So see if you can work through that. Okay, so setting up the proportion. Focusing on what you're looking for. If you know that you're looking for DHDT, that's gonna help guide how you want your volume equation set up. Because if I want to look for height, if I'm looking for DHDT, then I know that height will just naturally produce DHDT for me. So it just makes more sense to just get my equation in terms of height, which means that I want to find a way to replace R. Because I want to replace R in my portion equation. I want to solve for R so I can find a replacement for R. So replace the R with 3h/4. Don't forget, if you're replacing the R, the square is still part of the equation. Then go through and expand, clean it up all the way. Don't start doing DHDT because we're not ready, right? Let's get all the coefficients together. Let's resolve all the parentheses. Let's distribute the exponent through. Get the h's to come together. So one issue I see is sometimes I see students jump into the derivative too soon. And if you jump into it too soon, you're probably not going to remember all the product and quotient and the product and chain rule that's involved with that process. And that's going to lead to mistakes. So we shouldn't have to do all that difficult procedures with derivatives, because if we can clean it up the way we're supposed to, then the only thing we need is power rule, right? So this is where we want to be right before the derivative happens. All the h's pushed together, all the coefficients nicely combined together. And now you can go through your derivative. Okay, dvdt shows up, the hdv shows up, go through power rule with that h cubed. Then again, careful, anytime they give you the height or the radius of the water level, you want to hold till the end, because if we insert anytime sooner, we are losing a major property of this problem, which is the fact that the height and the water level is ever changing. We want to let it be stuck at a certain value until after we've established the derivative. So now once we have our derivative, now you're welcome to start inserting however way you like. Sometimes I would clean up a little further before I started inserting all the values, but once dvdt shows up, then everything is welcome to go in. So -2 goes in for dvdt, 30 goes in for h, and then you're just solving for dHdt. Careful, a lot of times these problems end up with pi in the denominator. Don't think of pi as just a notation at the end. It needs to be in the denominator if it lands there.
How do you know you can't just do the trick with the derivatives, where you just take the derivative of like r equals 3h/4?
You could. So you get drdt equals like this. But this is only really useful if you have one already known and you're trying to find the other one.
Well, you know dh, drdt, right?
Not
Oh,
yet,
no, we don't.
not yet, yeah. But let's say there was a part B that was asking for drdt, then you can do that shortcut. Yeah. But let's say it was asking for drdt and you misread it and you solve for DHDT instead, but then you went back and you realized, oh wait, it's actually for DRDT. You can also use this to kind of quickly get your answer as well, without having to restart the whole process. Okay, now what if this happened? What if I didn't tell you the height of the water level? What if I told you that the radius of the water level was 8? Good, so you're looking for height and you're saying, wait, I don't have height, how can I get to height? This is your, right, any of these, okay, any of these will help you convert a radius to height that you need, and then you can consider that. Okay, guys, I want to make sure that, that you take advantage of this extra day I'm giving you, so I don't want you to think of this as just, oh, I have a, quiz got delayed, so I can just wait till tomorrow to review. I want you guys to have this as an extra day, so I want you to treat tomorrow like as if tomorrow's the quiz. Do everything that you can, and that way you can really get that benefit of that extra day of review. Okay? But yeah, hope you get your phones. Spend today reviewing, have all the keys. Do as much as you can today.
Yeah.